So bond energies and bond length, we're picking up here, again, chapter 9. We talked so briefly about expanded octets. We're going to talk more about Vesper theory and like the names of different shapes and electron configurations or not electron configurations, electron groups and molecular groups. We'll talk about that later. But the last thing I'm going to talk about here are bond energies and bond length. Individual bonds can also be used to estimate enthalpy changes of reactions. The other ways we talked were like standard enthalpies of formation. So if you know that it takes this much energy to make like CO2 and it takes this much energy to make, I shouldn't have picked CO2. The amount of energy that it takes to make the individual molecules that go into a reaction, those energies can be used to find the energy it takes to make the product, or the comparative energies to make the product, right? Products minus reactants, enthalpies of formation. It's a similar thing with bonds. So anytime we do a chemical reaction, we're breaking bonds and we're forming bonds. And breaking bonds always requires energy. It always takes energy to break a bond. So that's always going to be a positive amount of energy. And a stronger bond is going to take more energy to break. Right? Makes sense. If you think of them like chains, right? If it's a really small, wimpy chain, it's going to be really easy to break. Doesn't take that much energy. If it's a really big, thick chain, you're going to need bolt cutters, and maybe big bolt cutters. So stronger bonds, harder to break. Breaking bonds, no matter how weak the bond, always requires energy. Yeah, it doesn't say it here. So then the flip side of that, though, is anytime you form a bond, it always releases energy. So when we take a compound, like here, it's just breaking this down, HCl, and then we're getting the individual atoms, hydrogen and chlorine. But if we were making hydrogen gas, H2 and Cl2, it would release energy to form those new bonds. So we have to input energy to break the HCl bond, and we would get some energy out for forming new bonds if this went from, let's do it as 2 HCl to H2 plus Cl2. All right, so there we're making the HH bond and a Cl-Cl bond. And so we would get some energy out. So the difference between a chemical reaction that's endothermic or exothermic is the relative amount of energy that you get for that you put into break bonds and then get out for creating new bonds. And that's the idea that we're going to use here to calculate the amount of energy that it takes to make new molecules. Now, not all bonds are created equal. So depending on other situations, how many things are attached to a carbon or other groups that are attached, the carbon-hydrogen bond is going to take different amounts of energy to break. So here, if it's carbon with 3 hydrogens, to break off one of those hydrogens would take 438 kilojoules to do 1 mole. That changes a little bit if it's carbon with 3 fluorines and 1 hydrogen. Then that hydrogen bond takes 446 kilojoules. Takes a little bit more energy. If those are bromine instead, then it's a little bit less. So we can average over a bunch of different types or situations for this carbon-hydrogen bond and get a value on average of 414 kilojoules. All right, so this is not going to be a perfect method, but let's say you're making a novel molecule or something and you want to get an average idea of the energies. You can use these average bond energies to figure it out. And then for double and triple bonds, I don't know if we talked about those yet. No, we talked about them last week a little bit. A double bond is stronger than a single bond, triple bond stronger than a double bond. Each of those will take more energy to break. So you can look at a series here. We've got a nitrogen double or single bond. That's going to take 163 kilojoules. If it's a double bond, it's 418. And the nitrogen-nitrogen triple bond is super stable. Will take 946 kilojoules to break on average. And that trend will follow for all of these. That if you have a double bond, it's going to be stronger than the single bond version. All right. So for any of these questions, you'll either have to be given values for these average energies, right? Not expecting you to memorize the whole table. They'll be given those values or given a table for a calculation like this. So using average bond energies, we can estimate enthalpy changes in reactions. So again, bonds breaking is endothermic or requires an energy input. Again, whether something is endothermic or exothermic depends on what the system is that you're talking about. For a chemical reaction, it's those chemicals. It's endothermic, we have to put energy in to break the bonds, but then bond forming is exothermic, so you get a negative bond energy. So to calculate the delta H of reaction, we add up all of the average energies for the bonds broken, and we add it to the average energy for the bonds formed. The sum of all those energies. I guess he asked this question, does the order matter? The order doesn't matter. Because the delta H of the bonds being broken is always going to be positive. The delta H of the bonds being formed is always going to be negative. So one's always positive, one's always negative. Doesn't matter which order you add those together. Yeah.
So in order to break a bond, you have to absorb energy?
The molecule has to absorb energy.
Okay. And to form a bond, you release energy?
It releases energy, yeah. Because that bonded state is more energetically favorable.
Oh, so you have to get rid of, I see that.
Yeah. So it's almost, I guess you could think of it as you feed them energy, you feed the two atoms energy to get them to separate. And then when they come back together, they'll give you that energy back to form a bond. Yeah. What's your analogy?
I just came up with it right now. Well, if you've got a molecule, you can think of it like two people, and they have a certain income, and then if you give them more money, they can separate and they can live separately. But then when they come back together, they don't need that extra money anymore, so they give it back.
Okay, yeah. I like it. I feel like it could, like a little bit of refinement, because it's like, why would they give up the extra money? And again, this kind of follows from this idea that changes in enthalpy are state functions, meaning that it doesn't matter how we get from A to B. The only thing that matters is the distance between A and B, or the change in energy from A to B. So we've got some amount of energy that it would take to break all of these bonds, or at least to break one of the bonds, I guess, here, because we're only taking one of the hydrogens off. And to break the chlorine bond, and then the amount of energy it takes to make the new bonds. And the difference between those two states, our products and reactants, is the delta H of the reaction. Yeah, so we always often say that energy is stored in chemical bonds, like its chemical potential. But it always takes energy to break a bond. It's just that when you form more favorable bonds, that's when you get an excess of energy. There's an overflow of energy. So it's always forming of the chemical bonds that releases energy. So a reaction between hydrogen and oxygen to form water is highly exothermic. Which statement is true of the energies of the bonds that break and form during the reaction? Highly exothermic. Yeah. Heard B out there. Yeah, so B, the energy needed to break the required bonds is less than the energy released when the new bonds formed. So you put a little bit of energy in. Yeah, I guess maybe, you can think of these like investments. So you're investing energy into the bond, and that breaks the bond. And then when that bond, no, stocks doesn't work. Yeah. Or you're like buying something, but then it's forming new bonds. So the new bonds release more energy than what you put in. So there was less energy required to break the bonds. You got more energy out.
And exothermic is positive, right?
Negative. You gotta put yourself in the place of the system.
So it's losing energy. So it's negative.
So yeah. So if you're the system, and you pay me, okay, let's put it in terms of money, right? So you pay me money, that's negative money to you.
Oh, okay. I like to think about it as
Yeah. So if I give somebody money, that would be exo. I was trying to think of like a word for money.
Economic.
Exo-economic, exo-financial, fiducial. I don't know. Right? Yeah. So that energy goes out, so it's negative. Energy coming in is positive.
Exo happy.
Okay, so a potential future fuel is methanol. Okay, so this is in the future. Re-recording this section because if you were there, you were there. And the correct way to do this problem, so talking about bond energies, is we first need to write out a balanced chemical equation. So since this is a combustion of methanol, it's going to be reacting with oxygen to form carbon dioxide and water. So this is our chemical equation, and we can take this now, and because we're calculating for kilojoules per mole, we don't have to worry about using fractions in our balanced chemical equation. So first off, we got to balance our hydrogens. So we'll put a 2 over here, balances hydrogens. Now we've got 4 oxygens on the right side. We've only got 2 on the left side, and we can put a 3 halves in front here for the oxygen. Now, the values that I'm going to use here for these bonds are coming from a table. So this is the table, but I've looked these up ahead of time. Go ahead and pause here, though, if you want to go ahead and try and find each of those bond energies yourself. And so the bond energies here are going to be based on the Lewis structures. So let me actually draw these Lewis structures out real quick. So for methanol, looks something like that. For oxygen, we're going to have a double bond there. For carbon dioxide, we'll get 2 double bonds. And those double bonds are important because double bonds contain more energy. Oops, hydrogen. So those are the molecules that we're breaking apart here. So we're going to go ahead and break every bond and then reform bonds in our products. So from our reactant side here, this carbon-hydrogen bond, we have 3 of those. So we're going to do 3 times 414, and that is in kilojoules. So we also have a carbon-oxygen bond. The carbon-oxygen bond is just one of those, times 360 kilojoules. And we're going to put the 1 in there just to be consistent. Now, we also have a hydrogen-oxygen bond, and that is going to have an energy of 1 times 464 kilojoules per mole. So per mole of those bonds being broken. Now we can move over to our oxygen. So we have an oxygen double bond, and that's going to be 3 halves, it's that coefficient, times the 1 oxygen double bond, times the energy of that, which is going to be 498 kilojoules. So all of these will be added together. And then if we crept over here a little bit too much. If we go over to our products now, we can say, okay, our products, we're going to be forming bonds. Now, the average bond energies on this chart are all positive. And that's because the sign of that amount of energy, whether it's positive or negative, is going to depend on whether or not you're forming a bond or you're breaking a bond. So for our broken bonds over here, that takes energy to break those bonds. For our formed bonds, we're going to be getting energy back out. So our first molecule here, bonds that we're forming 2 carbon-oxygen double bonds. So this will be 2 times, and this one actually has a special rule. It's 799, so negative 799 because we're forming a bond. And then for water, we'll have an oxygen-hydrogen bond, and we have a coefficient there of 2. So 2 times, and there's 2 hydrogen-oxygen double bonds in this molecule. So this will be 2 times 2. So 2 water molecules, each with 2 bonds, 2 times 2 times that negative 464 kilojoules for that. And now we can add those together, and that'll give us the energy that's coming out of the reaction. 2 times 414 plus 1 times 360 plus 464 times 1. Try not to make any typos here. Plus, and we do this 3 halves times 498. So that'll be 2,813 kilojoules that we'll have to put in to break those original bonds. All right, so that's positive. And then on our products, we'll get 2 times a negative 799 plus 2 times 2 times negative 464. So this will be negative 3,454 kilojoules. And to calculate the delta H of the reaction, this will just be the 2,813. I'm going to say plus a negative 3,454 kilojoules. And if I can get this right on my calculator, that's going to give us a delta H of negative 641 kilojoules per mole. So you're always going to break all of these bonds and then reform them over here, form all of these bonds from those component molecules. And this also even applies for the earlier example that we saw. Even though here they're only breaking one hydrogen bond, or saying that they're breaking one hydrogen bond and only breaking one chlorine bond, if we had broken all of these bonds, that would go up to something up here, and it would take more energy, right? So we would get 4 hydrogens plus carbon plus chlorine. But when we reformed those hydrogen bonds, essentially it doesn't matter that we only break some of those bonds, because if we put those 3 extra bonds in here from the carbon, from the methane, then we're going to remake those 3 bonds over here, and so that energy will essentially cancel out in the total function. So I think the safest bet when you're doing these problems is to break all of the bonds in your reactants, count for all those energies, and then reform all of the bonds for making your products. And if there's anything that you've done in there, it'll just be a little bit of extra work, but it'll ensure that you don't miss anything. All right, now back to the regular video. Bond lengths. The average bond length between 2 particular atoms and a large number of compounds, we can average these bonds. So the double bond is shorter than a single bond, and a triple bond is shorter than a double bond. They're getting closer together. And they get stronger. So bond length of a triple bond, carbon triple bond on average, 837 kilojoules. Double bond at 611. Single bond, 347. And of course, longer bonds are generally weaker, but there are exceptions, because there always are. So some more average bond lengths. And honestly, what these boil down to is the bond in this molecule shorter than the bond in this molecule. If it's a double bond, it's shorter. Good, and that rounds this out. Bonding in metals. I had those memes from last time, the my electrons versus our electrons. The electron C model of metal bonding is our electrons. The metal nuclei are all just sharing their electrons. It also explains why they're so conductive. It explains malleability and ductility too, because no single metal center is bonded directly to another metal center. It just needs to be around a bunch of metal ions or metal nuclei. So we can smash and deform them. They're malleable, and they're just moving around each other. Oh, the Lewis structure of ozone. I guess the Lewis structure explains this, but in ozone, it's got a double, oxygen has a double bond. Ozone has single bonds, and it's actually has a resonance structure. So both of these bonds are actually somewhere between a single bond and a double bond. They're weaker bonds, and they absorb UV light. So ozone in the upper atmosphere absorbs UV light, and then it breaks that bond. And you get oxygen with single bonds, and then the ozone reforms. So that's why it was a big deal when there was a hole in the ozone layer. because there was a lot more harmful radiation making it through the atmosphere. And that actually is already largely closed up. So, big win for environmentalism.
I thought you couldn't fix those.
What?
Because I remember, like, in elementary, they used to say